All right, students, A&P students, welcome back. This is lecture number 3 with the respiratory system. I doubt I'll get through all the way through the system with this short lecture, but we'll get as far as we can. Last time, I think I left off with talking about the ACE enzyme, angiotensin converting enzyme, in the pulmonary capillary section of the lungs. So we're going to move on to, we're still talking about the lungs. The next term on your note says pleura. That refers to a double-walled serous membrane that surrounds the lungs. So those two membranes, they're just like plastic bags. They're called the pleura, the double-layered serous membrane. Serous means fluid secreting. And the purpose of that fluid is to reduce friction of moving parts. So pretty much wherever we find moving parts in the body, we find serous membranes, like around the heart because it moves, around the lungs because they move, around the digestive system organs because they also move. Remember, the function of that fluid is to reduce friction from a moving part, just like the oil in the engine of your car. Now, the fluid from those serous membranes is actually secreted in the intrapleural space. So if we have a double-walled serous membrane, the fluid gets secreted in between those membranes into that space. Next topic, this is the next major topic on your notes, is called the physiology of respiration. That means we're going to talk about all of the physical activities and how they get accomplished. First, some definitions. Atmospheric pressure, that just stands for the pressure, the air pressure out in the atmosphere, out here, outside of the body. Atmospheric pressure, all pressures, as a matter of fact, are measured in millimeters of mercury. That's why you'll see mmHg. Hg is just the periodic symbol for mercury on the chemistry table. So all measurements are millimeters of mercury. That's with all pressures, including blood pressure, by the way. So atmospheric pressure just stands for air pressure outside of the body. Intrapulmonary pressure, that represents the pressure inside of the alveolar space, inside of those air sacs. Intrapleural pressure means the pressure between those two membranes of the pleura within that fluid secreting space. Intrapleural pressure is always negative to intrapulmonary pressure. It's always about 4 millimeters of mercury less than what's inside of the actual air spaces. The reason for that negative air pressure is to help keep the lungs expanded. It sort of sucks them out, sucks them open. So there's always that negative space. You've heard of somebody having a collapsed lung. Usually that's if that space, that intrapleural space, is compromised. Not to be dramatic, but if somebody gets stabbed or poked in the chest and that instrument goes through into the intrapleural space, that negative pressure is lost, and that causes oftentimes a collapsed lung. Boyle's law, next on the list. There's going to be a few laws named in this chapter: Boyle's law, Dalton's law, Henry's law. Boyle's law is P1V1 equals P2V2. Don't get hung up on this as an equation or anything like that. There's just a couple significances with the respiratory system that we use to apply it to Boyle's law. First, air volumes are inversely related to pressure. So anytime, for example, a volume in a space increases, the pressure within that space decreases. So pressure, volume are opposite, they're inversely related. Second, to learn from this equation is pressures always want to equalize. That's what helps with inspiration and expiration. So now I'm going to go through the steps of inspiration and expiration and as they apply to Boyle's law. So what happens during the steps of inspiration? First, the diaphragm, which is dome-shaped, to get my angle to the camera right. The diaphragm, when it's relaxed in the thoracic cavity, it's right below the lungs and the heart. It's dome-shaped when it's relaxed. When it contracts, it flattens out like this. So what we're doing when the diaphragm contracts, that happens. When the intercostal muscles between the ribs contract, our ribs go up and outward. So when these muscles contract, the volume in the chest expands. It increases. When volume increases, pressure decreases. So we get diaphragm contracts, intercostals contract, volume in the chest increases, pressure decreases, and because of Boyle's law, pressures want to equalize. Air literally gets sucked into the lungs to equalize the pressure of air with the atmosphere. Those are the steps of inspiration. The steps of expiration is pretty much everything just happens in reverse. These muscles, the diaphragm and the intercostals, relax. Elastic tissue causes them to recoil. So the chest volume decreases, pressure in that volume increases, and air gets forced out of the lungs. That's the steps of expiration. Physical factors influencing pulmonary ventilation. Step one is that there's three. So the first thing on the list is to memorize all three. And it's airway resistance, alveolar surface tension, and lung compliance. These are factors, physical factors, influencing pulmonary ventilation. What's pulmonary ventilation? Just breathing, moving air in and out of lungs. So what physical factors affect our ability to move air in and out of the lungs? First one, airway resistance. The book says this: conducting tube diameter decreases airflow as air flows from trachea to the lungs. What that means is anytime we shrink the diameter of tubes, like in the airway system, that increases resistance, makes it harder for air or anything to flow through that tube. Just like when we decrease the diameter of a blood vessel, resistance goes up. We decrease the diameter of an airway, resistance to airflow goes up. However, this is not really, that's theoretical, but it's in real life that doesn't really affect our ability to breathe. The reason is this: the body compensates for that decreasing tube diameter by increasing the number of tubes. So every time tubes shrink going to the lungs, we increase the number. Remember that respiratory tree, that upside down tree? Every time that we got a new branch on the tree and the tube diameters decreased, we got more branches. So that compensation in number actually makes airflow resistance by tube diameter decrease not really a factor in reality. Second factor, alveolar surface tension. So you know that there's moisture in the lungs. You know that water has surface tension. So anytime that there's a liquid, in this case water, there's going to be surface tension, and water molecules want to stick together. They're cohesive. How the human body gets around this difficulty is through the secretion of surfactant by those type 2 cells in the alveoli. So surfactant is secreted that decreases the cohesive properties of water, that allows the alveoli to stay open, and should they close or become shut, there's not a lot of water surface tension in there holding them shut. The surfactant allows them to freely open up again. Third factor is lung compliance. When you hear lung compliance, just think about the stretchability of lungs. So the higher the lung compliance, the more stretchable they are. So increasing lung compliance is a good thing. High lung compliance is good. That means your lungs are able to stretch and expand a lot. Decreasing lung compliance is bad. A normal healthy individual has lots of elastic tissue that's healthy, and their lung compliance is high. Somebody who has a disease like cystic fibrosis that compromises lung compliance, there's a buildup of scar tissue, fibrosis, that reduces lung compliance, and it makes pulmonary ventilation difficult. Case in point, coronavirus. The reports say that what this virus does, it gets into our mucosal membranes in our air passageways, also in our eyes as well, in the mouth, nose, and eyes, and it makes the virus replicate, makes its way down into our lungs, continues to replicate, and it compromises lung compliance, builds up fibrosis, fibrous scar tissue, makes it very difficult for people to breathe. That's why you're hearing all this talk about people needing to go on ventilators when they're at a certain stage of this disease, COVID-19. All right, takes care of that, which is good. We're moving right along. Next topic is respiratory volumes. Respiratory volumes is basically a list of memorizing different volumes that are measured within our respiratory system. First on the list is anatomical dead space. This is just the volume of air in the conducting zones that do not contribute to gas exchange. So, one thing that I wanted to highlight here that I would like you to pay attention to, and this is in your book, it's not in the notes, is alveolar ventilation rate. So look that up. What alveolar ventilation rate is, it's measured in milliliters per minute. What this is technically measuring is the real gas exchange that's occurring within our lungs every minute. And how that's computed is frequency of ventilation, which is just measured in breaths per minute, how many times you breathe per minute, and you multiply that times the difference between tidal volume and dead space. So if I take my tidal volume, that's the volume of air that's moved in and out of my lungs with every normal breath. If I subtract from that volume my volume of dead space, where gas exchange does not occur, I get that value in milliliters per breath. Then I take my frequency of breathing, how many times I breathe per minute, and I multiply frequency of breathing times tidal volume minus dead space, and that's milliliters per breath. That gives me my alveolar ventilation rate. Alveolar, so we've done anatomical dead space, alveolar dead space. The alveolar dead space is just the sum total volume of any blocked alveoli. So if you're a smoker, or if you have a cold or a cough and some of your alveoli are blocked from built up mucus, or they're not working properly, that's your alveolar dead space. Total dead space is just the sum of alveolar dead space plus anatomical dead space. All right, I already talked about tidal volume. That's just the volume of air that's moved in and out of the lungs during a normal breath. Normal range for that is right about 500 milliliters. Depends on your age, your genetics, your gender, male or female, your health if you're a smoker. The inspiratory reserve volume, IRV, that's defined as the volume of air that can be forcibly inhaled after a normal inhalation. That's much, much higher than tidal volume. So you take in a breath normally, you breathe in, you know and I know that you can forcibly inhale a lot more air, a lot more than a normal breath in when you're resting. That's inspiratory reserve volume. Expiratory reserve volume is just the opposite. That's the volume of air that can be forcibly exhaled after a normal exhalation. So you breathe out normally, then when you force your chest to contract and your diaphragm and you push out more air, that's ERV. Vital capacity is the total exchangeable air in the lungs. And what that is tidal volume plus inspiratory reserve volume plus expiratory reserve volume. So you need to know that equation. VC equals TV plus IRV plus ERV. And I want you to know how to compute IRV, inspiratory reserve volume. So how would you do that? If I give you a problem that says, for example, my vital capacity is 4,000 milliliters, my expiratory reserve volume is 1,900 milliliters, and my tidal volume is 500 milliliters. Let's do this on the board, okay? So if I give you a problem that says my vital capacity is 4,000, VC equals 4,000 milliliters. My expiratory reserve volume, let's say, is 1,900 milliliters, and my tidal volume is 500 milliliters. What's my IRV? This is how you compute that. You know this equation, VC equals TV plus IRV plus ERV. That's step one. Memorize this equation. IRV, all we're doing is rearranging this equation algebraically, sort of like when we did the MAP. IRV equals VC minus ERV plus PV. So when I give students this equation, this is what I recommend. If you're mathematically challenged, no problem. You take these two numbers up here, add them together, these two, sorry, ERV plus TV. So 1900 plus 500 is 2,400 mils. That's what's in the parentheses. My VC was given as 4,000. So I just take 4,000, subtract 2,400. What does that equal? Let's do the long math. 1,600 mLs. That's IRV. Okay. You can watch this video as many times as you'd like if you need practice with that. Last volume on the list is residual volume. Residual volume definition is the volume of air that cannot be forcibly exhaled from the lungs. So you can push out as much air as you possibly can voluntarily from your lungs, and there's still air down in that space. That is your residual volume. That takes a complicated math equation to figure out. It's not something we can measure directly. And it's done by your age, your weight, your gender, and all these other things, and based on your other volumes. I just want you to know the definition of residual volume. Gas exchange between blood and lung tissue. We're almost done for this video. Just going to talk for another 5 minutes. We know what Boyle's law is. It's P1 V1 equals P2 V2. It just tells us the relationships between pressures and volumes. They're inversely related. Basically, gas pressures always want to equalize. Dalton's law states this: the total pressure of a mixture of a gas is equal to the sum of each individual pressure. That's not complicated at all. Atmospheric air, for example, is not just made up of oxygen. In fact, most of it is nitrogen. So we've got mostly nitrogen, oxygen, and CO2 in atmospheric air. The vast majority of it's nitrogen, like 72% or something. All Dalton law says is the pressure of a gas, for example, atmospheric air, is equal to the sum of the gases in that total gas. So we take the sum of nitrogen, oxygen, and CO2, and that's the total pressure of atmospheric air. Henry's law states that when a gas is in contact with a liquid, gas will dissolve in the liquid in proportion to its partial pressure. So if we've got a liquid and a gas sitting next to a liquid, gases from or individual gases in the mixture of the total gas will dissolve into the liquid in the same ratio of its partial pressure within that gas. Example, atmospheric air. Let's just forget about nitrogen right now and just focus on the oxygen and CO2. So atmospheric air, when it comes into our lungs, oxygen diffuses out of our alveoli into our pulmonary capillaries because it's in contact with a liquid now, which is our pulmonary capillaries, it will dissolve into the liquid, the blood, in proportion to its partial pressure. So if the partial pressure of oxygen in atmospheric air is X, then it will dissolve into our blood in that same partial pressure. The only reason we give those definitions is because what comes next is 3 factors influencing external respiration. I'm going to go through those quickly and call this a day. 3 factors influencing external respiration. What's external respiration? It was defined at the beginning of this segment, not this particular lecture, at the beginning of the respiratory system chapter. External respiration is what's going on in the lungs. The exchange of gases between the air in the alveoli with the blood in the pulmonary capillaries. So it's oxygen uptake into the blood and CO2 discharge out of the blood. That's what external respiration is, and it occurs across the respiratory membrane. So here's 3 factors that influence the movement of gases across that membrane. So remember, oxygen's going into the blood, CO2 is going out of the blood in the lungs, and these are 3 factors influencing that movement. First, the thickness, your book says thickness, I prefer to say the thinness of respiratory membranes. So this affects the movement of gases. These alveoli are so thin-walled and they have such a high surface area that this enhances the movement of gases through that membrane. Super thin, so gases move easily. They diffuse. Oxygen diffuses into the blood, CO2 diffuses out of the blood fairly easily because the membrane is so thin and the surface area is so large. So red blood cells take about 3/4 of a second to travel through the pulmonary capillaries. We need to saturate that hemoglobin in those red blood cells in that amount of time. That tells us that saturation or movement of oxygen across that membrane has to be really fast in order to saturate that hemoglobin. All right, that's factor one, the thinness of the pulmonary membrane and the alveolar membranes. Number two, the partial pressure gradients and gas solubilities. Okay, what this says is that gases always travel down their pressure gradients. So this is not rocket science. When we inhale air, there's oxygen and CO2 in that air. When it gets down to our alveoli and our lungs, the pressure of oxygen in the air spaces of the alveoli is higher, is greater than the pressure of oxygen in the pulmonary capillaries. And gases always diffuse or move down their pressure gradients. So oxygen moves from the airspace into the blood because the pressure is higher in the airspace than it is in the blood. So oxygen moves into the blood. Likewise, the pressure of CO2 is higher in the blood than it is in the airspace, so CO2 moves out of the blood. Now, the pressure differentials are great in the terms of oxygen, but not very great in terms of CO2. Pressure of oxygen in our alveolar airspace is about 40 millimeters higher than it is in the blood. That pushes oxygen out of the air and airspaces into the blood. But the pressure differential of CO2 is much, much lower. It's only about 4 millimeters. So one would think CO2 isn't going to move very fast or as fast as oxygen out of the blood and into the air spaces. But this is not the case. And the reason this is not the case is because CO2 is much more soluble in a liquid than oxygen is. And that high solubility of CO2 in a liquid, aka plasma, makes CO2 move a lot faster from the plasma into the airspace, even though it's got a lower pressure differential. Last one, number three, is the ventilation perfusion coupling. When you hear that term, ventilation perfusion, think of ventilation means moving of air, breathing in and out. Perfusion means blood flow. So the ventilation part of this is moving air, breathing in and out, moving air into our lungs and out of our lungs. That's ventilation. Perfusion is blood moving across the pulmonary capillaries in our lungs. So as blood moves across the lungs like this, and air is coming in from ventilation, we have to get oxygen into the blood that's traveling by like this. So that's what the terms mean. Ventilation is movement of air, perfusion is movement of blood. What factors determine ventilation rate and perfusion rates are this. Carbon dioxide always influences breathing or ventilation. So the buildup of CO2 is what in our bloodstream is really what causes us to breathe, to move air in and out. It sends a signal to the respiratory centers and the pons and the medulla, and then that sends a signal to our diaphragm and our intercostals to move, to breathe. So CO2 is related to ventilation. Oxygen concentrations in the blood dictate perfusion. So oxygen dictates blood flow, CO2 dictates ventilation rate. And we need to saturate those hemoglobin molecules before all the red blood cells get across this pulmonary capillary bed. And as it turns out, diffusion of oxygen from the airspace into the blood is 3 times faster than the actual blood cells moving across the pulmonary capillaries. So if it takes a blood cell about 0.75 seconds to move across the pulmonary capillaries, and it takes oxygen only 3 times. It takes oxygen moves 3 times faster than that blood cell moves across, then we know that that oxygen is diffusing out and hemoglobin is being saturated in about a little over 0.3 seconds. That's really fast. Sorry, 0.25 seconds. Got my math wrong. Making sure I covered all my notes before we shut this down. Last thing is this, where it says pressure of oxygen controls perfusion. I already mentioned that. Take a note here. How pressures of oxygen control perfusion, blood flow is this. The pressure of oxygen controls perfusion by changing arterial diameter to different areas of the lungs where alveolar oxygen diffusion is best. So there are sensors in our capillaries that tell circulatory mechanisms to go where blood flow is the best, where air exchange is the best, and where blood flow is the best. So that's how oxygen sensors control blood perfusion. Pressure of CO2 controls ventilation by changing bronchial diameter to the bronchioles that are serving alveoli where CO2 is high. So in our alveolar spaces, wherever CO2 is high, the nervous system increases the diameter of bronchioles to the certain areas where CO2 content is the highest to get rid of that CO2 best. All right, that's where I'm going to shut it down today. The last lecture I'm going to do is going to be short and sweet. I'll probably try to do that tomorrow. That's going to be transport of respiratory gases in the blood, hypoxia, and CO2 carbon dioxide transport in the blood. That's complicated. Try to read it in the book. I will go over that, the 3 steps of 3 mechanisms or methods of transporting CO2 in the blood. That means from the tissues back to the lungs so that we can expel CO2. It's nighttime here. Everybody have a good night. Talk to you tomorrow.